Current electricity. The branch of physics which deals with the study of electric charges is called current electricity. Current is defined as the rate of flow of charges across a cross-sectional area of a conductor. The external energy necessary to drive the free electrons in a definite direction is called electromotive force, EMF. The EMF is not a force, but it is the work done in moving a unit charge from one to other. Drift velocity. Drift velocity is defined as the velocity with which free electrons get drifted towards the positive terminal when an electric field is applied. Current density at a point is defined as the quantity of charge passing per unit time through unit area taken perpendicular to the direction of flow of charge at that point. The current density J for a current I flowing across a conductor having an area of cross-section A is J equal to Q by T by A equal to I by A. Ohm's law. Ohm's law states that at a constant temperature, steady current flowing through a conductor is directly proportional to the potential difference between the two ends of the conductors. Therefore, I alpha V or I equal to 1 divided by R multiplied by V. Therefore, V equal to I multiplied by R, or R is equal to V divided by I. Resistance of a conductor is defined as the ratio of potential difference across the conductor to the current flowing through it. The unit of resistance is ohm. The reciprocal resistance is conductance. Its unit is mho, ohm minus 1. The electrical resistivity or specific resistance of a material is defined as the resistance offered to current flow by a conductor of unit length having unit area of cross-section. The unit of specific resistance is ohm, m. It is a constant for a particular material. The reciprocal of electrical resistivity is called electrical conductivity. The unit of conductivity is m ohm minus 1, m minus 1n minus 1. In simple circuits with resistors, Ohm's law can be applied to find the effective resistance. The resistors can be connected in series and parallel. Resistor in series. Let us consider the resistors of resistance R1, R2, R3 and R4 connected in series. When the resistors are connected in series, the current flowing through each resistor is the same. If the potential difference applied between ends of the combination of resistors is V, then the potential difference across each resistor R1, R2, R3 and R4 is V1, V2, V3 and V4 respectively. The net potential difference is V equal to V1 plus V2 plus V3 plus V4. By Ohm's law, V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3, V4 is equal to IR4 and V5 is equal to IR5, where RS is the effective resistance of the series combination. Hence, IRS is equal to IR1 plus IR2 plus IR3 plus IR4. RS is equal to R1 plus R2 plus R3 plus R4. Thus, the equivalent resistance of a number of resistors in series connection is equal to the sum of the resistance of individual resistors. resistor in parallel. Consider 4 resistors of resistance R1, R2, R3 and R4 are connected in parallel. A source of electromagnetic force, EMF, V, is connected to parallel combination. When resistors are in parallel, the potential difference across each resistor is the same. A current I entering the combination gets divided into I1, I2, I3 and I4 through the resistors R1, R2, R3 and R4 respectively. Such that I is equal to I1 plus I2 plus I3 plus I4. By Ohm's law, I1 is equal to V divided by R1. I2 is equal to V divided by R2. I3 is equal to V divided by R3. I4 is equal to V divided by R4 is equal to V divided by Rp, where Rp is the equivalent or effective resistance of the parallel combination. Therefore, V by Rp is equal to V by R1 plus V divided by R2 plus V divided by R3 plus V divided by R4. 1 divided by Rp is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 plus 1 divided by R4. Thus, when a number of resistors are connected in parallel, the sum of the reciprocal of the resistance of the individual resistors is equal to the reciprocal of the effective resistance of the combination. The temperature coefficient of resistance is defined as the ratio of increase in resistance per degree rise in temperature to its resistance at 0 degrees Celsius. Its unit is per degree Celsius. Ohm's law is applicable only for simple circuits. For complicated circuits, Kirchhoff's law can be used to find current or voltage. They are 1. Kirchhoff's current law and 2. Kirchhoff's voltage law. Kirchhoff's current law. Kirchhoff's current law states that the algebraic sum of the current meeting at any junction in a circuit is 0. Current flowing towards a junction is positive and current flowing away from the junction is negative. Therefore, I1 plus open bracket minus I2 close bracket plus open bracket minus I3 close bracket plus I4 plus I5 is equal to 0. I1 plus I4 plus I5 equal to I2 plus I3. The sum of the current entering the junction is equal to the sum of the currents leaving the junction. This law is a consequence of conservation of charges. Kirchhoff's voltage law. Kirchhoff's voltage law states that the algebraic sum of the products of resistance and current in each part of an closed circuit is equal to the algebraic sum of the electromagnetic force, EMFs, in that closed circuit. Here, current in the clockwise direction is taken as positive and the current in anticlockwise direction is taken as negative. Let us consider the electric circuit. Considering the closed loop A, B, C, D, E, F, A, I1 R2 plus I3 R4 plus I3 R3 plus I3 R5 plus I4 R6 plus I1 R1 plus I1 R1 equal to E1 plus E3. Both cells E1 and E3 send currents in clockwise direction. For the closed loop ABEFA, I1 R2 plus I2 R3 plus I2 R2 plus I4R6 plus I1RL plus I1R1 is equal to E1 minus E2. Negative sign in E2 indicates that it sends current in the anticlockwise direction. Wheatstone's bridge. An important application of Kirchhoff's law is the Wheatstone's bridge. Wheatstone's network consists of resistances P, Q, R, and S connected to form a closed path. A cell of EMF E is connected between points A and C. The current I from the cell is divided into I to the base of 1, I to the base of 2, I to the base of 3, and 4 across the 4 branches. The current through the galvanometer is I to the base of G. The resistance of galvanometer is G. Applying Kirchhoff's current law to junction B, I to the base of 1, I to the base of G minus I to the base of 3 equal to 0. Applying Kirchhoff's current law to junction D, I to the base of 1 plus I to the base of G minus I to the base of 4 equal to 0. Applying Kirchhoff's voltage law to closed path ABDA, I to the base of 1P plus I to the base of lower G, upper G minus I to the base of 2 are equal to 0. Applying Kirchhoff's voltage law to closed path ABCDA, I to the base of 1P plus I to the base of 3Q minus I to the base of 4S minus I to the base of 2R equal to 0. When the galvanometer shows zero deflection, the points B and D are at same potential and I to the base of G equal to 0. Substituting I to the base of G equal to 0 in equation 1, 2, and 3. I to the base of 1 equal to I to the base of 3. I to the base of 2 equal to I to the base of 4. I to the base of 1, P, equal to I to the base of 2, R. Substituting the values of 5 and 6 in equation 4, I to the base of 1 plus I to the base of 1Q minus I to the base of 2S minus I to the base of 2R equal to 0. I to the base of 1, open bracket, P plus Q, closed bracket, equal to I to the base of 2, within brackets, R plus S. Dividing 8 by 7, I to the base of 1, within brackets, P plus Q, divided by I to the base of 1P equal to I to the base of 2, within brackets, R plus S, divided by I to the base of 2, R. P plus Q divided by P equal to R plus S divided by R. 1 plus Q divided by P equal to 1 plus S divided by R. Q divided by P equal to S divided by P, or P divided by Q equal to R divided by S. This is the condition for bridge balance. If P, Q, and R are known, the resistance S can be calculated.